Welcome, welcome. I should probably make sure this is working. I should have done that before running on stage. Dang it. Okay, we're good. Yeah, because ever since we've had that audio issue, I've always had to make sure that we do not have any more audio issues. So I am live streaming this class. Purpose for live streaming this class is that, well, I am going to be covering the solution to the bolt problem at the very beginning, but also I'm doing this so anybody who is not able to attend the in-class session this week will be able to watch this. So let me go ahead and get started. At the very beginning of this class, I wanted to cover the bolt design problem I gave you last week. Now, as you all know, that was a super fun problem that pretty much all of you enjoyed. I got to hear whining from everyone, which is okay, because the purpose of that problem was not for you to pick the perfect bolt. The purpose of that problem is kind of threefold. First of all, I wanted to show you how challenging this class is. I gave you literally the easiest problem I could think of. And a lot of you spent several hours on this problem. And that was the easiest problem I could think of to give you. Okay? So that number one, show you how hard this class is. Number two, introduce you to bolt design. I didn't know how to pick bolts when I was in machine design. That was something I had to learn on my own. So guess what I'm not going to do to you? I'm not going to expect you to know how to do this without me telling you explicitly. Okay? And the last step is that, I really wanted to... Well, the last reason why I gave it to you is because it's good practice on being able to visualize physically what a system is comprised of, okay? Machine design is something that is so complex. It can be extraordinarily complex, but it can also be really simple. Okay, usually what people do when they get handed a problem like that, for the non-engineers, is they buy the 1-inch bolts, and they say, this'll do, which is probably 4 times stronger than it needs to be. But that's what they do. You just grossly over-design it, and you say, I'm pretty sure this is going to work. The end. The problem that I gave you, I'm not going to draw the whole thing, but was you have 2,300 pounds that you're carrying across a bolt that goes into a wall like this, where the bracket itself is 1 inch wide. Those are the only 2 things you need to know. Everything else that I told you doesn't matter. Okay? If you look at the bolt, the actual way the bolt is loaded, wow, that's a terrible bolt. Let me that never happened. Rewind your live stream. And then skip.
I just mean you have to watch it again.
Oh, dang! Cancel the live stream. Stop watching. Dang it. What you have here is you basically have 1 full inch on this bolt where you're going to experience any load. Now, generally what we're going to assume here is, to make this simpler, we could try saying this is 2,300 pounds of some kind of distributed load, which is realistic, but we don't know what that force distribution is going to look like. And quite frankly, we could spend a ton of time trying to figure that out, and it's not really going to give us a better answer. So instead, what we're going to do is we're going to say, all right, I know it's probably some kind of distributed load somehow, but I'm going to treat this as one load right here. And that one load is going to be 2,300 pounds. Okay? And this load is located 1/2 inch away from where this mounts into the wall. Okay? Now, in actual bolt design, when it mounts into the wall, you have the first 7 threads see the most tensile force. you end up seeing about a full inch inside that it is distributing the moment load in there. Generally speaking, if you're going to mount this into a wall, you want at least as much overhang out here as you have over here. It allows you to have the same kind of moment with the same kind of forces on both sides. But generally speaking, you can actually treat this as if the bolt is only this long and has a counter moment and a counter force in all directions. It's just generally how you can treat it. Okay? So really you only have half an inch that you have to carry 2,300 pounds. Now, I talked with my brother about this and I gave him the problem, and he kind of laughed at me and he said, this isn't quite a cantilever. This isn't a system that looks like this, because this can't move. The bracket is rigidly mounted to the wall pretty much with the tension. It comes from the bolt. You're not really going to be seeing any deformation out of this bolt in this half inch. You can basically treat this as if you're carrying a shear load, 2,300 pounds, and no moment. Which we know isn't true. There is a moment involved. But that moment, some of it's actually going to be carried by the bracket, because that bolt can't turn inside of the hole. If you make the hole tight enough, if you make the hole too loose, then yeah, okay, there's a moment. But basically, you're carrying 2,300 pounds of shear load. Now, when it comes to shear loading, your maximum shear stress, shear strength, is equal to half of the maximum tensile strength. That's just generally the assumption that we make. If you look at Moore's circle, if I were to draw out Moore's circle here, okay, if here is the shear strength that we're applying to it, 2,300 pounds, then this tensile strength here would actually end up being 4,600 pounds in tension. Okay, twice the value. So what we're dealing with here is you need to have a bolt that can handle 4,600 pounds of tensile load. If you can design a bolt that does that, you've got a bolt. That's it. Now there is a lot of other theory and considerations that we have to take when we're talking about this. We'll talk about that more when we actually get into discussing bolt design. But this is generally a problem that now I know what I'm looking for. I'm looking for a bolt that can handle 4,600 pounds. Maybe I say, let's go with a factor of safety. Let's go with a factor of safety of 3. So now I'm looking for a bolt that has 13,800 pounds. Okay, if I find a bolt like that, I'm good. Doesn't matter the material, doesn't matter the size, doesn't matter the threading. Now as far as the length is the other one that I'd have to pick. Again, I said I like to take a bolt and the amount that it sticks out is the amount that it sticks in. I'd probably want to make this be 2 inches long. Technically, a 1/4 inch bolt can't handle this. A 3/8 inch bolt should be able to handle this, grade 2 3/8 inch bolt. So what you would do is, I think it's a 3/8 16. The bolt specification would be 3/8 inch 16 by 2 inch grade 2 bolt. That's it. There is one answer. Now you pick a 1/2 inch bolt, yes, that's going to work. You pick an inch thick bolt, yes, that's going to work. You pick a 4 inch long bolt, yeah, that's going to work. Okay, this number has to be greater than 1. Hopefully everybody picked a number greater than 1. This number should be greater than 1/4 of an inch. Some of you picked 1/4 of an inch, which is fine. We didn't explain it, but generally this is what I would do. And this number here depends on this number, because this is the number of threads that happen per inch. 16 threads per inch is considered coarse threading. Coarse. I think it's 16. And then you'll have one that has more threads per inch that's called fine thread. So we'll get to that eventually again in bolts, but that's what it is. That's the bolt design. And I did that in 12 minutes. So there we go. Okay, so for those of you who watched just to see that bolt, we're now going to be getting into the class section of this. So feel free to not watch now. I already made a fool out of myself once. But that's every day, isn't it? Okay, what we're going to be covering today is we're going to be doing a review of mechanics and materials. Okay. So the purpose of having this review is there was a lot of that material that was covered in mechanics and materials. If anybody says otherwise, you didn't take the class. It's not in that class. There's just a lot of materials that were covered. And yes, I did have this class in mind when I designed those materials. Most of those materials, all of those materials, if you remember everything from that class, it's all relevant. We aren't going to be able to cover every bit of all of that material in this class, but I am going to expect that you understand most of the principles. Okay? So, whoa, okay, this is the second week of class. Hold on, I'm having an existential crisis. Last week we talked about a linkage. I threw up a jack on the board. I analyzed it, all the linkages. We talked about stress. We talked about just analyzing it through statics. Once you know what the forces through a component are, this is where we get into analyzing stress, deflections, that kind of a thing. Understanding failure, understanding factor of safety. All of you in this room have taken that class within the past year, so all of you have been exposed to this recently. I feel a little bit worse for the seniors who are in this class who have not taken the class as recently. But so you've got stuff. What we're going to start with is, let's say I take a section like this and I pull on it like this. Okay? First of all, this is called a tensile force because they're pulling outward. This tensile force is normal to the cross section here. So what we're going to call it is, this is a normal force. Okay? Or you could call it an axial force because this force is exerted on one end, and if we were to combine, if we were to extend out that vector, the direction of that vector falls in line with the direction of this vector. Okay? So that's a normal force. What happens when we exert this force is this force has to be carried by this cross section. Okay? If you imagine that this is a bunch of people holding hands, say everybody in here were to get together and violate COVID rules and hold hands, and somebody were to, at the very end of it, maybe be dangling off a cliff trying to help somebody, and then somebody on the other end is just pulling on them, trying to make sure that they all, get pulled. That force is carried along every member from one side to the other. Starts on one side, goes to the other. Now, if we were to zoom in on this portion right here, okay, where I'm taking my little camera and I'm zooming in, what you would see is these molecules or these atoms are exerting a force on each other. Okay? We go ahead and we call that a stress because it is a force per area. But ultimately, that's what it is. A stress represents the amount of force that is being exerted on a molecule or atom by an adjacent molecule or atom. It is the force that's being carried inside of this. Now, what you end up having in this type of situation is, if you look at the material really closely, the atoms all bond into very nice, neat structures called grains. The grains have boundaries between each other. But there are actually going to be holes in between the atoms and the molecules in this structure. They're small enough that you can't see them. You could do an electron microscope and you could scan a surface and you could find one, as much fun as that is. But they're everywhere inside of this material. Okay, this can be caused by having, so maybe these molecules here, and maybe you're missing an atom here. It can be just something like that, where now you have a hole where there's nothing. Pulling on this means that this material has nothing to pull on. And it causes these here to have to carry the load. If you pull too hard, this connection breaks. And it causes that hole to grow. This is what plastic deformation does. It expands the holes, but it causes the atoms to actually realign. So when we pull on this, the reason why we care about stress is because at some critical stress in failure theory, these cracks, that's what they're called, it's the technical term for them. I know it's weird, right? Like, hey, I have a PhD in studying material science. What are we going to call these weird holes in the material? Let's call them cracks. There we go. If you pull on this material hard enough, the cracks grow. That's it. At some point, you pull hard enough, and the crack grows at such a rate that it grows through the entire cross section of the material, and the material breaks. Okay, that is its ultimate strength. When we come up with standards for materials, what we're looking at is we're actually looking to see what the typical crack sizes are for that material and how much you can pull on it before those cracks propagate all the way through the entire material. Okay, so standard 1020 steel has a fracture strength around 32 kips per square inch. That's the strength of the material. You pull on it that hard, it will cause the material to break. Okay? So if you make a certain style of metal, you cool it a certain way, you can expect the crack sizes to be a certain size. Well, the reason in this class why we study stress and why we need to understand stress is because if you're designing something, you want to know when and how it's going to fail. If I'm designing an axle for a car and I just throw stuff together, you don't want to drive off the lot and have the axle just, the vehicle drops to the ground and all of a sudden, you become a real cool lowrider, but the kind of lowrider that shoots spark out the backside, your brand new car. You don't want to be that. You want to design your structures such that they are reliable, such that a video of your car fracturing and shooting sparks out of the backside as it drives off the lot doesn't hit YouTube, okay? That's what you want to make sure of. So it's really critical in design that we understand failure because we need to prevent failure. And sometimes we need to cause failure, but in controlled mechanisms. My brother works in roadside safety. One of the things that if you ever drive down the roadway, you hit something on the side of the road, you'll see guardrails, you'll see concrete barriers, and every once in a while you'll see like a concrete pylon, and you'll see some kind of a structure in front of it or something. It's called a crash cushion. That is intended to fail in front of your vehicle. As you smash into it, the whole thing deforms, the whole thing fragments and shoots things out of it. It has been carefully designed so that it fails in a controlled manner, such that, first of all, none of those materials fly through your windshield, because that might kill you. Second of all, so that that actually does absorb the energy of your vehicle. Otherwise, it's not doing anything. And third, so that it provides sufficient acceleration so that you can slow down in a quick enough area that you don't hit whatever it's trying to protect you from. You hit a concrete pylon at 90 miles an hour head first, your car will not look nice. However, cleanup, they could probably get out there with a spatula. It's dark humor. So in this axial force, how is force transmitted from one side to the other? How is that force carried? Well, we know we've got these hands between the atoms, because they're all bros hanging out in the same area. We know that they're grabbing onto each other and they're pulling, or they're pushing against each other. What's going to end up happening here is that at the very initial side of the application here, this force is only being exerted over a very small area. We're not going to be seeing any tensile force out here at the corner. There's no reason for there to be a tensile force out in the corner. Now, if this was a distributed load, where that load was being carried across the entire cross-section, then heck yes, you're going to be seeing a load out in the corner. But unless it's being loaded, that corner isn't going to be facing anything. But we know that about right here, this area is going to be in tension. Now, this varies from material to material, but anytime you have the stress, the force being applied through varying cross-sections, it is going to take a little bit in the material for that to transmit. Now, the stress here, the maximum stress in this component is going to be located right here, right at the point of application, because that is where the smallest area is. Okay, so for an axial force, a normal force, what it ends up creating is a stress that is normal to whatever that small cube is that we drew with all the atoms. Okay, so, right, I think I got ahead of myself in this lecture. Let's go ahead and quickly talk about a stress cube, which is just, if you zoom in, a bunch of molecules, atoms all hanging out. If we're going to draw just in the two-dimensional directions, we have all the total forces that could be exerted on this cube are right here. Now we can also have, these are your shear forces, these are your normal or your axial forces, okay? This is just in the two-dimensional area. We're assuming that this cross-section is really small. If you wanted to take an actual cube, you could apply a shear force on this face going upward, a shear force on this face going outward, shear force on that face going upward, which we already have drawn, shear force on that face going outward, which we already have drawn, shear force on this way going this way. There's just a ton of forces you can draw. It's not easy to draw, so I'm only drawing the two-dimensional version because it's just a little bit nicer. Okay, and we'll go ahead and call this is normal force Fy, normal force Fx, and I'm going to go ahead and call all of this V. V for shear force. V is typically what is used for the shear force. You know why you're laughing. Are you watching the live stream in class? Okay, well anyways. Yes, when you were a small child, your mother pulled at your legs and it caused your butt crack to propagate up your back. Okay? Does that make you feel happy? Oh, it's terrible. That is awful. Okay. So why is it that we have, when I exist a, let me try that again. Why is it that the shear force is 4 forces? These forces have opposites. These forces have opposites, right? That's the equal and opposite reaction. But why is it when I exert shear force V downward, I don't just have one on the other side that's opposite? Why do these other two show up? Because otherwise it would cause it to rotate. Okay? This force and this force create an opposing moment. If we're taking this square and it's in the center of this material right here, as soon as we start applying a shear force, you're not going to see that square start spinning rapidly. That would be really psychedelic if it did. But it's not being loaded with a moment such that it angularly accelerates. There has to be a counter moment on this. And that counter moment is created by the opposing shear forces. Anytime you have a shear force show up, a moment also shows up. Shear forces come with moments. Why? We'll talk about that in a second. Okay? So, here we have our axial force or our normal forces. On both sides, we have our shear forces. Let's go ahead and take this down to stresses now. Okay? A stress is just this exerted over an area. I like to again think of it as the stress is the force between molecules. Even though that's not really accurate, it's going to a small enough scale that it's studying how much force is being exerted per small area. So we have 4 real types of forces and moments that we're going to be dealing with. Okay? And I will distinguish the 4 different types for you. Type 1 is the normal stress. Normal stress is given by the equation sigma. Sigma indicates that it's a normal stress. It's pointing into the surface. Is equal to F over A, where force, it's how much force over how much area that force is being exerted over. Okay? So here, if we wanted to figure out sigma for this force, it would be how much area that force is being exerted over. It would be the area of the top of that box. Okay? How do we know that's a normal force? Well, normal forces, the axes of the normal forces align with each other. Okay? When I'm pulling on this pen, the direction I'm pulling in both in one way and the other, the vector forces that I'm pulling on it, they lie in the same line. It's basically a 2-dimensional entity. Well, 1-dimensional entity. It's on a line. Okay? They're both equal and opposite. If one of them is greater than the other, we have an acceleration. Otherwise, they're opposing. For this class, we assume that there are no accelerations inside of the material, because in order for there to be an acceleration inside of a material, it means the material is growing, usually exponentially, which is not good. It means your thing exploded. Okay, so to find out a normal stress, the axes align just like this. Okay, it happens when the forces align on that axis. That's what creates the normal stress. Okay? Now a shear stress, the formula for this is given by tau. Okay? Tau indicates that it is a shear stress. Whereas a normal stress like this, which I'm going to give you the sign conventions right now, if you were to take this square and pull on it in this direction. If it's a tensile load, then you're going to end up with something like this. Okay? This is called positive normal stress. If it's pulling out, if it's a tension load, causes it to stretch in that direction, then it is considered a positive load. If the forces exerted on it causes it to compress, squish inward, that's considered a negative normal stress. Okay? So again, if it squishes it, it's negative. If it pulls on it, it's positive. Okay? For shear stress, what you have here is tau is equal to 3/2 V over A. Now, the reason why that is because here, when we exert a force on this side and we exert a force on this side, all of the molecules really nice and neat carry that load between each other from top to bottom. However, when we exert a shear force over that same cross section, here this is a shear force. The reason why we know it's a shear force is because if you look at the axes here, here the axes align, here these axes do not align. They're not pointing at each other. There is a separation between the axes. Okay? So that's how we know this is a shear force. That's how we know that we are dealing with a shear stress. When this occurs, what you have is anytime you were to break this material, pull it apart, and study the total forces that are being exerted across that cross section. So we just temporarily break it, pull it back together. We're exerting a downward force. We're exerting a downward force here. An upward force is being carried across that cross section. And over here, here's your broken interface, and here's the rest of it. You have the upward force and downward force being carried across this cross section here. Okay, because this is equal and opposite. These two, while they both deal with the same interface, are going to be equal and opposite. If this is V, this is still V, but V is pointing in another direction, just depending on which face you're looking at. Okay, now the issue is, if you're looking at it right here, you don't have any upward facing forces at the top of the material, because there's nothing to push back down on it. So as you apply a shear force here, what you see is that the maximum shear force ends up being in the very center of this bar. It's located at the center of mass, or the centroid of the cross section. Okay, so what you have is, just looking at this, if I'm looking at the distribution of shear forces, at the top it's very small, at the bottom it's very small, and in the middle it's very large. The distribution kind of looks like a parabola. Small, small, large. Okay, but unlike this, the average shear force across that cross section would just be the force over the area. That's the average. But here, this now defines the maximum shear stress that is seen across the area, which is located right at the middle. So this is why this is 3/2 force divided by area. We're talking about maximum shear stress. Now, if you always only ever use 3/2 VA, you will always be designing for the maximum shear stress. So even if, when you're analyzing a component, if you're looking at the stress right here and you use 3/2 V over A, what you're looking at there is the maximum shear stress. You're going to be giving a conservative estimate for the actual failure. It's always okay to give conservative estimates when it comes to engineering. Okay? Conservative estimate means you know without a shadow of a doubt that's not going to fail, because a condition you put on there where I'm going to assume it's 3/2 V over A shear stress at this location at the very top of the beam, where you're going to see your maximum bending load. If you assume that 3/2 V over A occurs at that same location, then if somebody says, is it going to fail, you've done your math, you will always be able to say no with confidence. Because you made the assumption that shear stress is maximum here when it's not, but you over expected a stress at that location, you over provided the calculations, and now you can confidently say, yeah, I know the assumptions I made are too conservative. So, yep. It's okay to make those kind of estimates. There's a political joke here, and I just can't say it. Anyways, let's talk about bending moments. Bending moments create bending stresses. A bending moment is signified by a moment where the axes do not align. Here, these forces, the moment that's created by this is, so if I have a force here and a force here, and I have a radius vector between these where this is R, and this is F, and this is just also F. The moment that's created by this force acting at this radius is, the moment is equal to R cross F. Okay? Anybody remember how to do cross products of vectors? Trying to remember. It's, you end up having to do the whole I, J, K, component, and then you take this one, you multiply these four, you take this one, you multiply these four, you take this one, you multiply these four. It's gross. The resultant vector is perpendicular to both of these vectors. Okay? What vector is perpendicular to both R and F? Yeah, it's coming out of the Z direction. It's actually coming out of the board. That's the only way you can have one that's perpendicular to both. It has to be out of the plane. So the resultant moment vector has an axis that either comes out of the board or goes into the board. Now we can use the right hand rule here. If I were to put my right hand, the palm of my right hand in the direction of R and then curl it in the direction of F, what that means is that the moment that's being exerted, my thumb is pointing out of the board, that is the direction of the moment. Okay, so that's just right hand rule convention. It's what my physics teacher taught me in high school. It still remains true. So just a simple way of doing it. Otherwise, you can look at it and you can say, okay, if I were to try to hold this piece right here, this force would be wanting to make it rotate this way. Well, curling in that direction means your thumb is pointing out of the board too, so that's another way to do it. Okay, so with this creating a moment where now the moment here, this signifies it's coming out of the board. This signifies it's going into the board. With the moment coming out like this, the axis of the moment is located, now depending on where you're doing it, if you do your moment analysis from here, the axis of that moment is located right there at the force. Okay? That's great. Now we have to apply some kind of a counter moment to be able to counter that moment that exists. Now that counter moment, oops, I drew it in the exact wrong direction. That counter moment has an axis wherever it's applied, probably over here. Those axes do not align. If I look at a picture of this component, okay, and I got my shear force here, and then I apply a bending moment here, I can distinctly draw those two moments separate from each other on a top view because those axes do not align with each other. Okay, those points, they show up as points in this plane. Those points are not on top of each other. So a bending moment, your moment axes do not align. And again, you can draw them and have those moments not be on top of each other in this view. That's a good signal. That's a good signal that they're not aligning. Okay? Here, a bending moment creates a stress sigma. Some people write sigma b, and that value is equal to my over I. Where this is the moment, y is the distance from the centroid of that shape to wherever you're analyzing the force, the stress at, and I is Ixx is the second moment of inertia of that cross section. Okay, so if I'm looking at this, the distribution here, this y that's being put in here means that the stress varies across the cross section. Just like what we talked about over here where the stress varies across the cross section for the shear force, the maximum value is right in the middle. The stress varies across the cross section also for a bending load. What you have is, going to go ahead and erase this. For a bending load, if I have a component like this and I exert a bending load like this on both sides, what's going to happen is that's going to create this type of bending in the component. Now that's grossly exaggerated, but that's what the bending load does. This line here is shorter than this line right here. Is that going to be in tension or compression? If a line gets shorter, is that tension or compression? That's compression. The top of this component in bending is in compression. This line right here is a lot longer than this one right here. Is that going to be in tension or compression? It's in tension because it's being stretched. So what we have here is by applying this bending moment, we have the top is in compression, we have the bottom is in tension. And at some point in the middle of this line is the same length as this line. Meaning it's not in tension or compression. So the bending moment creates a weird stress distribution on that cross section. If we break this cross section, what you end up seeing is applying this moment, applying this back moment. What happens is you have at the top it's in compression, and at the bottom it's in tension. Okay, it actually creates a triangular distribution where right here the stress at the center of this component due to bending is 0. Now this does create an interesting problem when we're dealing with components that are both in bending and experiencing shear forces, because where is the location of the maximum shear force? The maximum shear stress in this cross section? It's right in the middle. Where is the location of the maximum bending stress? It's at the top and bottom. So in reality, this maximum shear stress does not occur at the same place as the maximum bending stress. They occur at two different places. The bending stress is 0, where the shear stress is maximum, and the shear stress is effectively 0, where the bending stress is the maximum. That's interesting. But this is also why I go ahead and say again, assume that the shear stress is constantly 3/2 V over A. You can assume that the shear stress is 3/2 V over A at the top and bottom. It'll give you the most conservative estimate, even though it's not true. Oh, I forgot to draw my diagram over here. So here, if we experience a shear force like this, a positive shear stress is going to cause it to look, I believe, oh, I didn't bring my textbook today. Dang it, they have the sign conventions. But I believe the positive causes it to look like this, and the negative causes it to look like this. I may have to issue a correction next class. Forgot to bring my book. Okay, so a positive shear stress causes a component to get a little wacky, and if significant enough, it just droops on the right side. A negative shear stress causes it to rise on the left side. So that's just general convention. Obviously, if you just flip the problem around 180 degrees, your positive shear stress becomes a negative shear stress. So it's not really that exciting. Bending moments, again, you issue a bending moment on both sides of this. It's going to cause a positive bending moment, causes a happy face. A negative bending moment causes a sad face. Okay? So that's 3 of the 4 forces and moments that we're going to be dealing with in this class. I'm going to cover the last one real quick, which is torsional moments. If I were to, on this diagram, if I were to take this and I were to say, okay, on this bar, I am going to apply a moment here, but the counter moment is going to occur on the back side of this bar at the same location. If I draw them in this view, you end up with something that looks like this. They're both on top of each other. I mean, we can shorten the arrows so at least. So now it's they're both on top of each other. This doesn't tell you anything. And in fact, this moment load does not exist outside of this real central area. You don't have some moment that's needed over here or here to counterbalance that. These axes are aligned, and this is called the torsional moment. Okay? Because they're aligned, you cannot draw them nicely in this view. The best way to draw it would be, say here's your bar, is to draw, this is how you draw a torsion. It has 2 arrow cross sections. Okay? We'll talk about the stress for torsion at another time. I don't remember the formula for it. Yeah, that's great. Now, the thing is, it is possible to have a torsional moment create a bending moment. A good example of this is, let's say I have a crankshaft. Okay, where the component looks like this. We got a round bar, and that round bar connects to your crank. Okay, and maybe it's welded right there or something. Okay, we're gonna spin this shaft in this direction. The axis for that moment goes along the center line of that beam. Problem is, there has to be another moment on the other side of there to counterbalance it. So it's creating a torque on here that is in this direction. You got that counterbalance right here. But then what you need over here is you actually have to have, so this transmits to that, which these are both facing the same direction, and then this counterbalances this. So even though this component is in torsion, the torsional moment creates a bending moment here. Got to think about what direction that is. That's into the board. Okay, so what this is going to do is your component's going to look something like this. Okay, it's creating a bending moment in this component. And we have that torsional value, the moment created by the torsion, is the bending moment here for that other component. So what we're going to be studying the next few weeks is how to really pick out the bending stresses and everything in this. Okay, you do have an assignment that is due next Friday. That assignment consists of a reading assignment, which I haven't posted yet, a couple of worked out problems, which this is the first time now I'm assigning you book problems for this class, and a quiz. Last week your quiz was bolt design. This week your quiz is based on the lecture materials I gave you this Monday. Okay? So, 3 assignments, quiz, reading, homework. I will see all of you on Friday. Otherwise, I will see you in the live stream on Monday. Enjoy your weekends.